here we go. Oh yes, there's a lot to do for this first one. Yeah. Is this a topic that you've seen before? Electric fields. Yeah, it's kind of it's advanced enough. So there's quite a bit to get through. But anyways, let's get started. So you all know this from chemistry. Electric charge, and we talked about this before, I'm sure. Electric charge is a basic property of electrons, protons, and other subatomic particles. And you also know that electrons are negatively charged while protons are positively charged. I'm not telling you anything new, I would hope. So anyways, nothing to make note there. Also, I don't think I'm telling you anything new if I tell you things are negatively charged and things are positively charged pull on each other, and this is what makes the electrons and the protons stick together. Things at the same charge, what happens? They repel. Again, I don't think I'm telling you anything new. Okay, but now on to something new. So, an electric field, no, before you write it down, because there's some words I'll have to explain here, like a vector field. An electric field is a vector field that shows the direction that a very small positively charged particle will move when placed in the field. Now, before you write anything down, let me explain with an example. So, for example, imagine you're thinking about the wind here, and let's say you have a little wall here, and let's say the wind is blowing here, okay? And you put a little mass here, it'll blow that way. Put it here, it'll blow that way. Put it here, it'll blow that way. But if you put it here, it might not move, because it's behind the wall. Or here, it might not move. Or here, it might move at a little angle. Maybe down here, it'll move even more. Did you get what I'm drawing here? It's like I'm drawing all the possibilities, you know. Maybe here, it'll move like this, and maybe it'll move like that. You see, this is what we call in physics a vector field, these red arrows. This, in fact, this example here will be a force vector field. It shows you all the possible forces you could have depending on where you put your mass. Now I don't know. I think this is new, but I think it's easy idea. What do you think? Is it okay?
Charge is just replace the wall with the point charge.
Yeah, well, I'll give you another example, okay? So like if you have a river, and there's a rock in the river here. Yeah. So you can all picture that the river flows this way, but there's a different direction around the rock, like this. So what would happen if you put a small stone here? Will it move up or down? It'll move this way. And if you put it here, will it move up? No. It'll move this way. These are vector fields. These diagrams, these pictures. Yeah. So an electric field is a vector field for charge. So for example, suppose I have a positive charge here, a big one, and I put a small positive charge here. Which way will it move? This way, won't it? And what happens if I was to put the charge closer? More. And then less, and then less, and then less, like that. Okay. So all these arrows together, you can picture all of these arrows together. That diagram is called the electric field. Yeah? I think you would have seen something like this in high school, maybe, with the magnet under the piece of paper. You pour the iron filings on it. Yeah. Okay, so if you want to write that down, it's important that it's a positive charge that's used in the diagram.
So for fluid we do electric fields and gravitation.
Yep.
Same formula, just Q is replaced with similar.
No, it's similar, not the same actually. Okay. You got that? Yeah?
Not yet.
Okay. Not too difficult of an idea, right? So I think it's okay. You got that, Zach?
Almost.
Okay. A little rainy outside. There's a rainbow now. Can you see it?
Oh.
Kind of. It's very faint. Very hard to see. Can you see it?
It's gone now.
I can see it from here and through the second window.
Oh, okay.
Can you see? No? Can you see it, Dorian? Yeah?
Is a triple rainbow possible? Because I've seen a double rainbow.
Yeah. Yeah. I'm sure I've seen that once. I definitely have seen double. Okay. Now, I don't know if you drew a diagram as an example already. So, just in time. I'll still mark you present, but if your friend Diego comes in after you, he gets marked absent. What was I saying? Oh yeah. So here's a good example diagram. Now, imagine here I put a small positive charge. What will happen? It will get pushed away, repelled, yeah. And if I put a small positive charge here, for example, attracted. Okay? If I put it in the middle here, it will zip over to the left here. Okay. This is a good example of an electric field. I think you should have this with your definition as an example. Oh yes, we'll have the awards ceremony later today, won't we?
Yeah.
You'll get to see some of the engineers from last year, maybe.
Is it the people who got the highest scores or something?
I think so, yeah. And in fact, now I'm not 100% sure, but I think one of the students, not only did he get the highest score at this centre, but I think he got the highest score in all NCUK centres.
Wow.
Which is very impressive considering how many NCUK centres there are.
How do you know? Do they look at the total marks or something?
I think it's the total points or total scores, average score or something like that.
A few people getting
A stars.
stars.
Yeah, I'd say they must take the average score.
Okay.
I believe he had a fantastic physics teacher who single-handedly helped him achieve this. All right, continue. Yeah. Okay. Now, I think we talked about this when we did electricity. How do we measure charge? We use something called the Coulomb. Yeah. Now, the Coulomb, oh, actually, let's see if you remember. We did do this. Does anyone remember the definition of a Coulomb?
Is the amount of, wait a minute,
It's definitely the amount of something.
electron,
Oh, no.
no?
And does have something to do with flow, actually. Yeah, amount of charge for what?
1 second or something.
There is 1 second in it too, yeah.
How many charges move how many in 1
Ah,
second?
no. Off track now.
Okay.
Yeah, go on. I think you know, Gina. Go on, tell us. Yeah, amount of charge a current can carry. Yeah. The amount of charge a current can carry in 1 second. You just left out one word. Do you know what you left out? She nearly has it perfect. The amount of charge carried in a current in 1 second. What are we missing?
1 ampere current.
Yeah. It's a charge transported by a constant current of 1 amp in 1 second. You nearly had it, Gina. And then that's the value for a proton, and that's the value of an electron, and that's the value of a neutron. That's right, Dorian. You look a bit confused by this.
No.
No, you sure? It's okay?
Yeah.
Oh, I'm sure Diego's just late because he's buying roses for everyone.
Oh.
That has to be the reason, right? See, I was thinking ahead yesterday when I was going home. I decided I better buy my flowers now. Otherwise, if I do it tomorrow, well, what happened to you?
I'm pissed.
Yeah, why? What happened to you? Come on, give us a good reason. Now, don't tell us the bus, because that's a boring reason. You always tell us the bus. It is the bus?
Yeah. Major disruptions on our
No. You have such bad luck with buses at 9 o'clock.
I don't know what happened with the 122 bus, but it's always.
Where the heck's my Valentine's gift?
I'm here.
Ah, yeah. Anyways, I bought my roses yesterday.
Excuse me?
I bought my flowers yesterday because I knew if I do it this evening going home, there'd be none left. So I was thinking ahead. And I actually got the last bunch of 100 roses in Lidl.
Wow.
And they are much cheaper than the florist. Much cheaper. Alright, have we got that?
Yeah.
And it was funny, when I was paying as well, there were 4 men in front of me also buying flowers. So as a joke, I said to the guy in front of me, "Excuse me, is this the line for paying for the flowers?" Because it seemed like a few people had the same idea. Right, have we got that?
Last one.
Do you do Coulomb in chemistry or not? No, doesn't come up in chemistry. Does Lorraine just say +1 -1?
Yeah.
Yeah. Now you might also need the masses. No, you will also need the masses. I don't know if you have them. So mass of the proton is that, and electron is about 1,000 times smaller, and then the neutron is actually more or less the same as a proton.
How are these calculated?
There are 2 experiments that are used. The results of the 2 of them are used. One of them actually, for example, the electron. One of them you would have done, I think, with Lorraine. mass to charge ratio.
Yeah.
Oh yeah, yeah, it's fructose spectrometer.
Yeah, that experiment can give you the mass to charge ratio. Then there's another experiment called, oh, what's his name? Oh, something like Milkowski or somebody. Oil drop experiment.
Oil drop.
Yeah, it's where you have charged oil being dropped in an electric field, and that experiment gives you the charge of an electron. So if you know the charge of the electron and the charge to mass ratio,
Yeah.
then you can get the mass. Yeah. Yeah, we'll actually talk about those later in the chapter. Okay, continue.
Yeah.
So, oh yeah, and sometimes we write charge as the letter E, which is a constant, not to be confused with the maths E, or +1, as in chemistry. All right. Different parts of the field will be stronger or weaker than other parts. After all, we talked about this. The small charge will fly away faster if it's nearer to the large positive charge. Okay. This gives us the idea of what's called an electric field strength. So if I go back to my picture here, here the field is stronger than here. And where it'll be weakest, maybe out here, for example. Okay. So we need a way to measure the strength, how strong the field is. And the way we do that is quite simple. The electric field strength, which we used as the letter E, is simply defined as the force per charge, or the formula F per Q. The bigger the E, the more force per charge, the stronger we say the field is.
If is not constant.
Yeah, so it's the electric field strength at a point. Oh, you're running out of paper then. You're on your last page.
No, I just.
You going through it backwards?
Yeah, because I bring the wrong notebook.
Ah, okay. Got you. Okay, you got that? No, not yet. Yeah, got that? Yeah. Okay, so what are the units?
Newtons per Coulomb.
Newtons per Coulomb, obviously. Yeah. Fair enough? Makes sense? Yeah. Okay, continue. Now, here's a very simple one I think you can do. A current is running through a wire, and in fact there's an electric field around the wire, and what you do is you put a little electron near the current, and there'll be a force it experiences. And how much force? I give it to you. I'll give you this much force here. And my question is, what is the electric field strength? So the formula is F over Q. Do we know the F? We do. And do we know the Q?
Yes.
Yeah, what is it?
E.
E, the charge of an electron. So, taking out your calculator, you can give me the electric field strength. So let me think. I think that should be a pretty big number, shouldn't it? It would be pretty big. What you got, Lynn? 10 power minus 25 over the E, the charge of it.
What's the E?
Why is it over?
1 point. No, it's times. It's what
Times,
is the
because
force?
you want the force.
No.
What?
Yeah. What is the force?
Oh, I'm
now?
sorry. I'm not.
And
Oh
the
my
distance
goodness,
from
I'm
the
not
line.
even reading my own question right. This is disgraceful. I'm so sorry. I've given you the E, haven't I?
Yeah.
I've given you the E. My goodness. Wake up, Stephen. I've given you the E and I want the
Force.
F. So F equals EQ. Yeah, so I'm so sorry. It should be very small.
How do you get the distance?
The distance? Oh, not necessary. The formula doesn't have distance.
At this distance.
Yeah. Yeah. Sorry, what's the F?
10 times 2 to the. Oh.
Gina's going to tell us. Go ahead, Gina. Yeah, I made a dog's dinner of this. E equals F over Q. So F equals EQ. The E is,
1.602
yeah.
times 10 to the minus.
what is it? 1.60.
That can't be right.
No, that sounds right. Times 10 to the.
Minus 44.
Yeah.
Yeah, because there's 2 minus.
Mm.
Yeah, it's tiny. Well, it should be small. It's only an electron. Yeah? Is that okay? Sorry, made a total dog's dinner of that. Okay. Here's a better one. I'll read my own question more carefully. An electron is placed from 3 protons. So let me draw that. You have 3 protons, proton, 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 and an electron. The strength of the field is that. So here the field strength is 1.41 times 10 to the minus 24 newtons per coulomb. And which direction is the field? Oh yeah, actually, which direction is the field here?
Towards the electron.
No.
In or out?
No, it's in because it's.
It
positive
is
charge. No,
out.
it's yeah.
There you go. You gave me the wrong answer, even though you realised what I was trying to trick you with. The electric field arrow is always how a positive would move
Yeah.
in the field. So I know it seems a bit weird to draw it outwards. The electron is moving opposite to the arrow. Yeah. Anyways, I've given you that. Oh, and this is an electron. This guy here. And my question is, what is the acceleration?
Easy.
Yeah. Yeah, so you said F over M, didn't you? And F is EQ over M. And the E we know, and the Q, now, is it 1 or is it 3?
It says, doesn't say.
No, I suppose my question is, do I use the
Yeah.
Q here, or do I use this one? This Q or this Q?
The Q where it's where the point charge, where the electron.
Yeah, so is that 1 electron or 3 protons? What value do I use for the Q?
The electric field strength
Yeah.
of the 3 protons.
No, it's 1 electron. It's the Q of the thing that is experiencing the force,
Even,
not the thing that's causing the force.
even though we're trying to. Wait,
Well, yeah, that's what it did. Why am I saying otherwise?
You're doing things right, but saying the opposite
I
this
know
morning.
what's going
Yeah.
on.
And the mass, is it of 1 electron or of 3 protons?
1 electron.
Good. Okay, so what did you get, Zach?
2.48 times 10 to the minus 13.
Did you get that as well? Ah, we don't have, yeah, okay, if you want,
Well, direction.
yeah, if you want to put in the direction, I'll put in towards
The protons.
protons, yeah. Or if you want to say minus, then Gina, you're saying that this way is plus and this way is minus. Yeah. Yeah. Okay. Is that alright? Yeah? Continue? Continue?
Yeah.
Yeah?
How much newtons per coulomb over?
Say again?
Newtons.
Are you trying to figure out the units?
Yeah.
Yeah, so it would seem that this is newtons
Per
per
coulomb. Times coulomb.
yeah, they
Yeah,
cancel.
they cancel newton and
Newtons per kilogram is the same as meters per second squared
Yeah.
because it's force over a mass. Okay, a small dust particle of mass 1 milligram and charge of minus 100 E is placed between 2 horizontal plates. The plates produce an electric field. The small charge is held balanced between the 2 plates and doesn't fall. How strong is the field? So I'll draw what's happening here. You've got 2 plates and you've got a little charge here. It's of 1 milligram and its charge is minus 100 E. By the way, from chemistry, if its charge is minus 100 E, does it have an excess of protons or electrons?
Electrons.
It has an excess of electrons. In fact, how many electrons? It has an excess of 100 electrons. That's how it has a charge of minus 100 E. Now, it doesn't fall, does it? I say it's balanced. But there are 2 forces acting on it. What are they?
Gravity.
Yeah, the weight. And so there must be an upward force here caused by the electric field. Right? And this force here, what would be the formula for it? E times Q. Okay. And finally, which direction is the field? Is the field going up or down?
Are they both positively charged?
Both?
The plates.
Oh, I'm not telling you that. I don't need to tell you.
Well, they would be opposite to each other if they're the same charge.
No, don't be thinking about it like that. Okay, let me help you. This is negatively charged, true?
Yes.
Which way is the field pushing it?
It's repelling it.
Is the field pushing it up or down?
Up.
Up, because it's cancelling the weight, right? The field is pushing it up, but we don't draw the field arrows going up. Why not? Because it's a negative. And the field arrows are in the direction of a positive charge. So in this diagram, the field is drawn like this. Okay? Because if I put a small positive charge in it, it would want to move down, because the small negative charge wants to move up in the field. Is that okay? You're looking a bit confused.
Doesn't the question say they're both the same charge?
Did I say that? No, I just say 2 horizontal plates. I don't say anything about their charge. But now that we're talking about it, Zach, which is the positive plate and which is the negative plate?
Positive at the top.
But we'll talk about that later. Okay, do you have enough information to get the weight? You do. Now, the weight, not the weight, the E. The weight is equal to mg. Now be careful, that mg is milligram. So milligram is, oh my goodness, what is it? A gram is 1,000, a millionth of a kilogram.
Yeah,
a millionth of a kilogram times 9.81. Okay, you have enough info now to get me the E, because the E will equal F over Q, which will equal 10 to the minus 6 times 9.81 over 100 times E. Yeah, yeah, that's why the hundred's there. Yeah. Right, did you get an answer?
Yeah.
What is it?
6.12.
Yeah.
Times 10 to the 12. Is Newton per Coulomb is a vector?
Technically, I think electric field strength is a magnitude. It's how strong the field is, not a vector. I think. Although you could easily make it a vector by simply including a plus or minus direction. Yeah. You know, Zach, I suppose technically maybe it actually is a vector, because when I think about the formula E equals F over Q, F's a vector. So if I don't want this to be a vector, then I need to say the magnitude of F.
Yeah.
Oh, okay. Can I continue? Dorian? Yep. Continue? Okay. That's a silly question. Right. Different charges configured in different ways will produce different electric fields. We'll look at 4 types. Point, sphere, parallel, and dipole. So anyways, you can write them down as you go through them. So the first one is a point charge electric field. You have this one already. That's fine. You don't have to redraw it if you don't want to. But maybe you should write its name beside it. This is a point charge electric field. No, it's not. What am I saying? That's 2 points.
Yeah.
Dirty liar, Stephen.
So,
What? This isn't parallel plates. Why are my names wrong? Alright, sorry. That is the sphere. That is a point. Oh my goodness. And that's a dipole. Oh my goodness. Right, sorry. Something went very wrong with my names on these slides. Right, you have this one drawn. Its name is actually this lad. The electric dipole. So you want to write that name down. How the heck did that happen? I do not know. Let me fix this. The first one is called the dipole. Okay, now the next one, that's called point. So this one here that I want you to draw is called point. Now, please note, these are two separate diagrams. They're not the same diagram. So this is what you would look like if you have a plus, and this is what you would get if you have a minus. But of course, you know, if you did have the two of them together, you don't get this picture, you actually get this picture, okay? So I think when you draw this, perhaps you should put a line down the middle here or something to separate the diagrams, okay? This is a point charge. Point charge. I should say.
So can we quickly go back to the dipole?
Yeah? Okay, do you have those drawn? Right. The next one I have, what's this one? Yeah, it's a sphere, not the parallel plates. So that one there, that's the sphere. It's the same as the point, just bigger. Okay. And the last one here is not the dipole. This one is called the parallel plates. Yeah, this last one is not the dipole, it's called parallel. That's not how you spell parallel.
It is.
Oh, it is. It just looks weird.
Yeah, something looks like it should be two R's, hey?
Yeah, not parallel points, parallel plates. This is actually like the example I did earlier. If you have a positive charged plate and a negatively charged plate, you get this electric field between the plates.
Sorry, the sphere one is just called the sphere?
I think just spherically charged, perhaps.
Spherically charged.
Yeah, if you want the full name, spherically symmetric charge. Okay, you got that? Yep. Now, there's something I need to add to those diagrams in a moment, something called the equipotential lines. And it's the part of space where every point has the same potential energy. Now, before you write that down, I just want to draw what I mean by it, okay? So, let's take a very simple example. Here's the ground, and then here is a mass, and I'll put the mass here. And this has a potential energy, right? Is there anywhere else I could have put the mass so that it has the same potential energy? Yeah. I could have put it here, or even here, or here, and they'll all have the same potential energy. So this line here, everywhere around it has the same potential energy. I could call it like PE1. This line here will have a different potential energy, right? But at least everywhere on the line has the same potential energy. So maybe you could call this like PE2, something like this. These lines, they're called the equipotential lines. They're the part of space where every point in it has the same potential energy. Now, I'm not saying, of course, that these two lines have the same potential energy. I'm just saying everywhere on the line has the same potential energy. Okay. So you'll need this definition, and in a moment we'll draw in the equipotential lines.
Say every point charge in it.
I suppose, yeah, given the context, I felt not necessary, but yes. Well, no, actually, Zach, because this definition holds for gravity or any other situation. Yeah, so it doesn't have to be a charge. Okay, shall we draw in the equipotential lines? Because I should explain, in the exam, what is very normal is they ask you to draw one of those diagrams and the equipotential lines on it. So I'll start with the last one. What was the last one I gave you? The plates, wasn't it?
Yeah. It's just a bit parallel to line.
Yeah, there. You had the positive plate and you had the negative plate. So what you can add to your diagram in a different colour if you want are these lines. These are the equipotential lines. Just add in horizontal lines. Do you have a different colour, Lynn? Or maybe, you know what, maybe you could put it in as like dots or something. Okay. What was the second last one I did? The sphere, was it? Yeah, well, the sphere and the point have the same diagram.
It's a concentric circle.
Yeah. The equipotential lines will look like this around them. The last one is the dipole, which is kind of hard.
Oh, they go like.
Yeah.
They're not straight.
Yeah.
It's further after the weaker field gets.
Yeah. Okay, let's try and draw it. Right, which should I put on the left, the plus or the minus?
Minus.
Like this, yeah? And I know there's a big arrow towards the centre, like here. And then you have arrows coming out like this, don't you? And then going in here. And then what's happening? It kind of curves around here, doesn't it?
Yeah.
I'm not going to draw them all. Right. Okay. How do we do this again? Well, it's definitely. Don't draw this yet. It's definitely circular on the halves here. But then it starts to change here. So.
Goes closer.
Oh, I know this. Hang on. It's. Oh yeah. Hang on.
Yeah, no, it would be like.
No, hang on. Let me think. I can do this. I think there's a horizontal line down, a vertical line down the middle here.
Vertical?
Yeah, there's a vertical line down here,
Just in between the roof.
and then it goes. Then. Oh my goodness. What am I doing? Yeah, it's like this, I think. Oh my goodness.
Yeah, that's right.
Yeah.
Closer in the middle, the line.
Yeah, they kind of get a bit stacked up, don't they? It's really hard for me to draw. You know, the easiest blooming thing would just be to get a Google image. You get the rough picture. Don't draw this yet. Let's get a nice Google image to help us draw it. You're right. I think these guys get kind of stacked closer together on the right. You kind of get squished in. But let's get a Google image. Right. If I have internet in here, do I? I think so. Okay. No, not equidistance. Here we go.
Thank you, Mom. Anyways.
Here we go. Let's see.
Oh, so they're like ovals, actually. Yeah. That's nice.
Yeah. Yeah, the green one is the, oh dear, the green one's the equipotential. Let me get a better picture.
That one with the red.
Here? No, here?
That one on the left.
This one?
Yeah.
Ooh. No, I don't like that
Looks
one.
like a
It's like this
owl on
this-
acid or something.
spirographs. Here we go. This looks like a, this is an easy enough one to draw. Right, can you all see that? That's what I was trying to draw. These are the equipotential lines for the dipole. That's what I was trying to draw.
X and Y axis name.
I think whoever made this was drawing the equipotential lines and they had the coordinates of the positive and the negative. So I think this is just like an XY coordinate graph, and they were plotting it in some software. That's what I'd say. I'm just trying to get the shape for you to draw. Okay, did you draw that, Lynn? Yeah. Yep. Okay, can I close this and go back to the slides? Okay, so, I don't know, did you write down the definition as well? You have that? Yeah, okay. Right. When a current is passed through two conducting plates, separated at distance d with a potential voltage V, then, okay, so if you go back, what diagram was the parallel plates? The last one? Yeah. We have a special formula that lets us calculate the electric field strength for these plates. Okay. Yes, you could use F over Q, but what if you don't know the F and you don't know the Q? Well, we have this formula. The electric field strength in the parallel plates is V over D. So what happens to the field if you bring the plates closer together? Does it get stronger or weaker? Stronger. And if you use a bigger battery, higher voltage, it also gets stronger. How do you make the electric field? It's very simple. You have your two plates. You usually have a vacuum here. And you just connect this up to a positive. And then just connect the other side up to a negative. And that's it. That's a very simple way to make an electric field. You know? So, I think you should make note of this formula. Now, there is something missing from this definition, which I should actually tell you. You know the electric field strength will be different at different points. So, I think what I've just given you there is the full strength if the particle was at the top. But it doesn't really...
Is it the distance from the center or the top?
That's the D. Yeah. That's
not the distance between the particle and the positive plate. That's what I thought it was.
Oh, you're making it more general. So like if the particle was here, you'd use that distance.
Yeah.
Maybe. I don't know. It's not something I worry about because in the exam, the particle always begins at the top.
Yeah.
I don't think they require you to consider the particle. Well, I mean, it's impossible. The particle can't just suddenly appear in the center. It usually what happens is this gets dropped in from the top. Anyways, it's not a big deal because for exam purposes, it's just this. But now that I'm thinking about it, what do you do if you put it in the middle instead of at the top? Yeah, I think you're right, Zach. It would be then half the distance. Maybe. Maybe not. No, Zach. No, I think the D is always the distance between the plates.
But E is not constant, that's why I don't understand.
No, I think. No, Zach, the E I think is constant between the plates. It's a uniform strength.
Not if a positively charged is placed right below. Right
No, but
next-
see, think about it like this, okay? If the positive charge is placed further away from the positive plate, that doesn't make the field weaker because it'll be nearer to the negative plate. It's being pushed down from the top
Yeah.
and pulled from the bottom. If you place it near the top, it gets more of a push and less of a pull. If you place it near the bottom, it gets more of a pull and less than a push. I think in total the two balance, so you get a uniform strength. Yeah. I also have another reason why I know it's uniform. That's in a later class. There's a reason as well because, well, no, I'll tell you later. Yes, sorry, to answer your question, that D is the distance between the plates and not the distance between the particle and the plate. But it's the same thing because it always begins at the top anyways. So that is the plate distance. Okay. Continue?
Yeah.
Right, now, what about if you have a point charge? So for example, you have a point here, and you've got a little point here. Which one will have the stronger field, the blue or the red one? The red one. So whatever the formula is for the E, it must have a distance in it.
D, R.
Yeah. It must look something like this.
Looks like Q1, Q2.
Not quite this.
Not that one?
Will the field be bigger or weaker if this charge is bigger or weaker? What do you think? If this is bigger, will the field be stronger or weaker here?
Stronger.
So then we think the Q must be on the top. Okay, so anyways, you could think about this and you won't be surprised to discover that when you have a point, the electric field strength is given by this formula. Now this guy here is a constant. Okay, I'll need to give you the value. E is a constant, its value is that, and as a little exercise we'll work out what the units are of the E0, epsilon 0 here.
Yeah, it's the same as like the gravitational constant, right?
It has the same role as that.
Yeah.
You see, Zach, that comparison is part of the reason why I know the plates
No,
is uniform, because it's an analogy to a gravitational weight,
Yeah.
which doesn't vary on the height.
Oh, yeah. Makes sense now.
Let's work out what the units are.
Is that 4 pi epsilon?
Yep,
50?
0.
Epsilon 0.
Yeah. Right, shall we work out the units? So the formula is E equals 1 over 4 pi epsilon 0 q over r squared. So that means epsilon 0 is 1 over 4 pi E q over r squared. The units on the right will be coulombs. E is, what do we say, newtons per coulomb, and the r is meter squared. So that can come up the top. And the units are coulomb squared per newton per meter squared. That's the units there for it. Okay?
What was the value again?
I'll switch back there.
8.85.
Okay, continue.
The unit was coulombs.
There it is there. Coulomb squared per newton per meter squared. Okay? Yep. Now, I don't know why I gave the student the name. A student named Ben puts an I think I remember why. A student named Ben puts an electron between two parallel plates of voltage 100 volts and 1 centimeter apart. What is the force acting on the electron? So I basically want you to use these two formulas. F equals EQ and E equals V over D. And I want the F here from the electric field. Okay? So I'll give you a minute. You can. It shouldn't take you too long. I'm not being clear. I want only the electric field force. I don't care about gravity. I mean, you could include the gravity. It's so small it won't make a difference. You got an answer?
Yeah.
It's going to be
1.6.
F equals EQ equals VQ over D. Yeah. And that's going to be 100 times the charge of an electron divided by the distance. Did you use 0.01?
Yeah.
Okay, so what did you get for the force?
1.602 times 10 to the minus 15.
Yeah. Yeah. Okay, fine. Yeah. Next. Two horizontal plates have a potential difference of 200 volts across them. The positive plate is a centimeter above the negative plate. So it's like this. Again, positive, negative. How long would it take half a milligram of charge 1010E to fall from the top to the bottom? So there's a small positive charge here, and it will fall quickly or slowly to the bottom. Quickly. Why?
It's being repelled.
By being repelled by the positive, attracted to the negative, and gravity. So my question is, what's the time? How long will it take to go from the top to the bottom? Okay, so I'll give you a minute for this one. My tip is first get the force, then the acceleration, then the time. Yeah? Force first.
Thinking about something. So, it doesn't really have to do with this, but if molecules are attracted by gravity,
Yeah.
why isn't the air, like all the mix of air, which is oxygen and nitrogen, all compressed here in the bottom part of the air?
I think what happens is, as the air settles and compresses, it pushes back. Yeah, because
Bounces.
yeah, kind of.
Okay.
Like an elastic material. Like if I try to squish anything down.
But gases, you can compress them.
Yeah,
So,
but you still need a force, right?
yeah.
And they always push back if you compress them too much. So it just means that the weight of the gas isn't heavy enough
To compress.
to compress it all the way down.
Okay. And that's why we have 1 atmosphere of pressure here at sea level.
Yeah,
Because it's compressed, but not.
compressed, yeah.
Acceleration is distance over time squared, right?
Are you using S equals which formula? Just give the ATS.
You have to use S equals ut plus half at squared.
To get the acceleration?
Yeah.
No.
No?
No, use S equals MA.
That's what I did. I got A.
Oh, good. So now you're getting the T. Yeah,
Yeah.
fine, yeah. Who else has answers here? No, it's another minute, Zach.
Okay, no, that's seems very wrong. What did I do wrong?
Did you get an answer then?
What was the big T?
Hmm? Oh, okay. What did you get?
It was volts, right? Or was it millivolts?
No volts.
What did you get?
I got 1,766 seconds.
Ah, Zach,
Yeah.
come on now, that's ridiculous, and you know it is.
Yeah, I know, that's what I said.
How would it take that? Oh no, come on. Okay,
9.74 times 10 to the power negative 8.
that seems more plausible. It should be a minuscule time.
What did you get? Different?
Let's have a look, guys. Let's have a look.
Oh,
Okay.
No.
Well, look, we'll do it now, anyways. So, F equals EQ, right? And E is V over D times Q. Okay? So far, okay? And F is also equal to MA. Therefore, A equals VQ over DM. But you also know that S equals UT, which is 0, plus a half AT squared. Okay? Now, if I want, I should have really have said, but it doesn't actually matter. Let me just go back in time. There's actually two forces, EQ and MG.
Oh, yeah.
Right? No, listen. This number is so much bigger than this number, it actually doesn't really matter. Okay, but, I mean, if you want to include it, you can. But it doesn't matter because, I mean, this will be a small number because the mass is so small, yeah. And this will be a huge number because the charge was so large, 10 to the 10, you know.
Oh, 10 to the 10, that's why I got it wrong.
All right. So, this is equal to VQ over D plus MG, and that's equal to MA. So the A is equal to G plus VQ over MD. But like I said, this this is so big compared to G, it shouldn't matter. It shouldn't matter at all. And S equals UT plus a half AT squared. And what am I looking for? The T. The T is 2S over A. Yeah? Root. So the answer is the time will equal root 2S. And then the A is 9.81 plus 200 plus, no, times, what was that? That couldn't have been, it's a Q.
That's a Q.
That's a Q, my goodness. Times 10 to the 10 times
1.6.
yeah, E over half a milligram.
Damn it.
Yeah. Times D. Right. What do you get when you type all that in?
Not mine.
Not yours, okay. What did you mess up?
I squared it instead of square rooted it.
Oh.
0.016.
0.016
And 6?
seconds. Sorry, Zach, what is the E as well? I'll put it in. 1.6 times...
2 times 10 to the minus 19. E, 1.602 times 10 to the power of minus 19.
Then the minus.
19. At least I didn't get syntax error this
Yeah.
time.
Are you happy with that or not? Dorian, you're checking this?
Wow.
She's checking. We're going to see if I did anything... No, actually, if you did anything wrong, because you gave me the 0.016.
Yeah. Come on, did it go?
I think it's 200.
Syntax error? Yeah.
200.
200, so it's this one.
Maybe because did we round it off somewhere?
Can I see what you typed in on the calculator?
Oh, it's gone now.
Is it?
It's gone because I
I can't go back?
I don't know.
Oh, I can't go back.
Change.
Alright, I'll type it in. 0.02 over 9.81 plus another fraction 200 times 10 power 10 times 1.602 times 10 power minus 19 over 0.5 times 10 power minus 6 times 0.01, and you are correct. 165 seconds.
Oh, it's because we added the entry in this one. Okay.
Can I go back actually? How much of a difference would taking the 9.81 out make?
0.01, because we got 0.017.
It doesn't make much of a difference.
Gives
Well,
me 0.0178 something.
Oh, it does matter a little bit. Yeah, okay. So if you did leave this out, you would get 0.0177. Okay. Okay, it made more of a difference than I thought. Fair enough. Fair enough.
So should we take...
In this example, the difference did matter. There are some examples where the difference is like 4 decimal places away, so it doesn't matter.
Okay.
But it turned out, I thought I gave it a big enough charge for it not to matter. Okay. One more example here.
What's wrong? You have to put brackets.
Brackets one.
Everywhere.
Right.
No, it's not creation, it's a line.
Proton, electron, distance here, 10 to the minus 10 meters. What type of motion will this make? It'll move around in a circle. In fact, what have I just drawn from chemistry? Yeah, which one?
Orbital.
One is
No,
orbital.
Ah, yeah, but which atom? Which
Oh,
What?
hydrogen.
hydrogen? Isn't it?
Yeah.
Yeah. Yeah. So my question is for you to do now. Give me the time, periodic time for an orbit. Yeah.
This is circular motion again. I've forgotten all those formulas.
Zach, will I be wasting our time if I let everyone try this, or should I just give the answer now?
I think Dorian will have a go at it.
Yeah.
What
Where is
what
the circular
formulas do we
motion
need?
formulas?
Oh, look, you're no, okay, hang on, I'll do it now. You're all frantically looking up your formulas. Let's have a look at it. So, look up, guys. Guys, the time.
Oh, you get A and then you can. Yeah.
The time is 2 pi over omega, right? That was one formula. And F equals m omega squared or.
Yes.
Yes. Or I think in the formula book it was F equals ma and A equals omega squared or. So F equals m omega squared or. So omega equals root F over m or. Right? If I put that in there, I get T is 2 pi root m or over F. F is equal to EQ. But what's E equal to? 1 over 4 pi epsilon 0 Q over R squared times the Q. Now I have to be careful, these Q's are different because one of the Q's is for the electron and one of them is for the proton. Yeah. However, it doesn't matter because it's the same charge. So both of these is E. So that's 2 pi root mass of the electron times the radius, but there's an R squared here, so that's radius cubed, if that comes up the top. Oh, hang on, I'm running out of space. 4 pi epsilon 0 m R cubed over E squared. Right. That's the time.
Do we have epsilon 0 as a...
It was the constant.
Oh, number 32.
Oh yeah, on the calculator.
Mass times...
And that's mass of the electron. Mass of the electron. Oh, so actually that E squared cancels, so you could actually write it as just 2 pi over E. Oh, and that 2 pi, oh, okay, it doesn't matter. Root 4 pi epsilon 0 m E or cubed. I can keep cleaning it up, can't I?
Syntax error, how do you...
What's the value of epsilon?
I gave it to you earlier.
3.95 times 10 to the minus 16.
10 to the what?
16
Positive or minus?
minus.
It should be small, but I don't know if it should be that small.
Oh, 2 pi over E, my bad.
Yeah, okay.
Oh, okay.
Well, Zach, you could have used That or that. I don't mind. It doesn't matter.
With the masses.
Dorian,
Hmm?
no, give me the calculator. Look, you have all these constants on it. Mass of the electron is constant 3.
Yeah, 32.
Epsilon, there's the charge, 23. And epsilon 0 is 32.
Ooh.
You don't have to look up in your notes. That's why I recommended this calculator.
Ah. Apparently here.
Yeah, so look.
Oh, but I hope.
No, let's clear it. Right, so look. Guys, look. I'll do my... Okay, root... Okay, 2 pi over e, which is shift... How do I get constants? Shift mode, is it? Shift 7, isn't it? Shift 7. Okay, so I need e. What number is e? 23.
32.
No, the 23.
32.
20.
Huh?
Oh, yours might be different, isn't it?
23.
23. There's the e, okay? And then what have I got here? 4 pi. Right, what one is epsilon 0? 32.
Yeah, sorry.
And then mass of the electron is
3. 0.
O3. And then radius, that's 10 power minus 10 cubed. There you go. Yeah, that's right, Zach.
3.94.
3.95 times 10 to the minus 16. Yeah. Handy, right?
But do we get to take this?
Yeah.
Okay.
However, this means that your answers will be more accurate than the marking scheme, because the constants built in on the calculator.
Perfect.
Yeah. In the exam, they're not.
That's why I don't do it, because if you'll be off by quite, like if the value is 3.95 times 10 to the minus 16, you can get like,
Yeah.
4 point something.
yeah.
What's 4 point something?
No, it could be rounded off to 4 point something to the 10 to the power negative 16.
If we use less accurate constants, yeah. Right, that was a hard one. Well, was it? I don't know. What do you think? Lynn is nodding. That was a hard one.
Maybe dig up this, if you were waiting for me to get the
I'm gonna try just
2
see
pi
if I
over.
use it.
Okay. So that was the last example. I'll let you try these questions for a few minutes now. Okay. So if you want to open up the workbook.
How many questions more?
Opening.